than I do, but I'm going to try and take it back to some basics and share with you, I hope, a more general approach to the problem of energy and consumption. I, in a past life, and indeed still practice in radiology as a medical practitioner, and for many years I taught medical students how to read a chest X-ray. And one of the things that I would commence my lecture with was a comment that in general terms people would only take away 3 key points from a lecture and remember that in the long term. And subsequently I stopped teaching that because one of the 3 things they took away was that there would be 3 things. So I'm hoping tonight that you take away 2 others. Now we've had 4 speakers already, and so I'm, if you like, I'm the last speaker for the opposition, and I'm trying to wrap the debate up. And so I'm going to endeavour to remember at least one point from the other speakers. So John, my take-home point from you is that it's like going back to the 1880s. It's a war between AC and DC, and it'll be interesting to see how that plays out. I don't think it's a war. I think it's actually a cooperative arrangement where there's always a technical solution which is best, and then it's a question of is it affordable. Going back, Chris, I guess the take-home message for me is that hydro is a valuable resource, but it's a long way from where it's being used. And if I had to encapsulate the issue for hydro as I see it, for hydro to work, you need 2 bodies of water, very large bodies of water, that are approximately 100 metres separated in vertical height and in horizontal position very close to one another. So there's really only a few places in Australia where that applies, and in those locations it also has to have rainfall in order for those large bodies of water to fill or be rejuvenated. So hydro in itself is a valuable component of the system, but it certainly won't be the dominant process in Australia, where we simply don't have enough high mountains and low valleys filled with water. Going back from there, I think Megan taught me that I would now be able to pronounce Neo again. That's fantastic. That's a wonderful take-home message. Kate, unfortunately, I've remembered that she's only in the job for 8 weeks, and that's going to stay with me for quite a while. Look, I'd like to move away very slightly from my topic, and I don't know how to go forward, so I'm going to press the space bar so it happens. So from radiology, I went into renewable energy, and in brief, as a radiologist, I entered the field of interventional radiology and then into pain management. And that's a very valuable skill to have, relieving people who've had back pain or neck pain or shoulder pain. They're intensely grateful. And for about 8 years, I worked in New South Wales, in Orange and Broken Hill. Living in South Australia, it's quite a challenge to travel between those locations. And after a few years of commercial travel, I got the bright idea that I would teach myself to fly and get a plane, and I would fly back and forth, which I did because the summer in question was beautiful, calm summer with no thunderstorms, and it was lovely. Subsequently, I learned to fly and ultimately flew in instrument flight rules at night. And in the course of learning to fly between Adelaide and Orange, which is about 3 hours and 12 minutes, plus or minus headwind, the only thing you had to do along the way was remember to change the fuel tank every hour. And the rest of the time I had thinking time. So for the first time in many years, I was able to sit quietly and think. And at the time, I was amazed that the little plane that I was in was travelling at about 12 or 14,000 feet above the Earth, and it was travelling at about 400 kilometres an hour, and it was using less fuel than a Ford Falcon would take to drive across the Hay Plain. And it caused me to wonder how an engine could be so fuel efficient. And I'd like to give you a few little take-home examples of energy along the way, because we talk about these very large numbers, and it's a bit like the American debt. It becomes meaningless when you get to 22 trillion. So the fuel tank of a car might have 50 litres or thereabouts of usable energy, and each litre is about 100 kilowatt hours of energy. So the average car is driving around with something like 5,000 kilowatt hours of chemical energy in the tank. And if you compare that to a Tesla, high-end S, for example, with 100 kilowatt hours, your average Holden has got about 50 times as much energy in the tank. Now, an internal combustion engine is very fuel inefficient, but nevertheless, that Holden can drive across Australia without hesitation, whereas a Tesla car has to stop and refuel every 200 or 300 kilometres. So it takes me to that point of energy storage is in fact our biggest single problem if we accept the existing paradigm. And what I'd like you to think about tonight, if I get time, is to consider the possibility that we should change the paradigm, not simply run faster and faster in the same direction. So if we accept that in South Australia, the energy demand in the summer is around 3,000 megawatts continuously through the summer. If we have 4 hours of sunlight and we have 24 hours to cover, we're going to need 6 times that amount of energy. We're going to need 6 times 3,000, so 24,000 megawatts of energy production just to meet the daily demand of South Australia. And if we're going to store energy for 2 days, we're going to have to double that storage capacity. And if we're going to store it for 4 days, which is not uncommon, South Australia can have 3 or 4 days of cloud, we're going to have 4 times that. We are into enormous amounts of storage of energy in order to meet the demand if we continue to use energy the way we are at the moment. So looking at that problem, sitting in my plane flying across Mildura at the time, I thought, what are the options? We can either make storage of energy very cheap, or we can change the way we use energy, or we can collect it more cheaply and therefore be able to afford to live with the style that we are now used to. So with that in mind, we went down the path starting about 12 years ago now. Jeff Phillips, who's at the back of the room, runs a fantastic engineering shop, and he decided that he would take me on as a customer and that we would build a turbine which ran on very, very low temperature steam. So we had the idea that I would collect heat in the form of hot water, turn that water into very low pressure steam, and then drive a turbine. The idea being that I could store the hot water during the day and produce electricity at night, so meet some of the baseload demand. Because the storage cost of hot water is in orders of magnitude about 2 cents per kilowatt hour, it's cheaper than any battery by an order of magnitude. So it seemed to me, at least as a starting point, that it would be worth considering hot water as a storage medium because it's very cheap, very plentiful, and available everywhere. So we went on to build a turbine, and Jeff assisted me in manufacturing very many prototypes using every known form of turbine, and ultimately we settled on a multi-stage axial flow turbine which was able to operate with an input temperature of somewhere over 80 degrees centigrade, and it was more effective over 100 degrees centigrade, but that took me into the realm of steam as opposed to hot water, and water under pressure is effectively an explosive medium. So we worked very hard to create a turbine which was able to operate at that very low pressure and low temperature range. The downside was that it gave me a very, very large amount of warm water as the waste product at the end of that process. And so I turned my attention to how I could use warm water in a valuable way rather than simply attempting to deliver it back to ambient with no economic value. So we built the turbine here, and we have operating prototypes, but I then sidetracked, if you will, onto how I could use the hot water more valuably. So some 4 or 5 years later, with a great deal of modelling in the meantime, we developed a concept of an occupied building which was able to use less input energy and therefore be sustainable. So my first little message to you was about the amount of energy in the fuel tank of an old vehicle, no longer with us. The second little suggestion that I'll leave with you is the question of, if I took a typical road with cars travelling along it, and I wanted to plant corn or some other crop on either side of that road and use the corn, turn it into alcohol, for example, or distill it and make hydrogen with it, it doesn't matter. If I wanted to plant crops along the side of the road with sufficient energy collection to power the vehicles driving along that road, would anybody like to hazard a guess as to how wide the field would need to be on either side? So somewhere between 2 and 8 kilometres is the answer. So every road would need a very, very large paddock on either side of it. It's simply not practical if we continue to use energy the way we are at the moment. So I thought, if we bring that back to buildings, if we look at the amount of energy that a rooftop can collect, and it's driven by obviously the sunlight falling on the roof and the number of hours of sunlight per day, and roughly 4.1 or 4.2 hours on average today over an annual cycle. If we look at the amount of energy that I can collect off that rooftop, and my plan is to power the building from its own roof, what does the building need to do? What does the envelope need to do? What do the internal components of that building that are consuming energy need to do in order to make that a sustainable process? So what we came up with was a building, and I don't know if I've got my little pointer. A building that collects energy off the roof. Go forward again. And up the roof we have here 100 kilowatts of PV panel at the rear, and we have around 150 kilowatts of solar thermal collected at the front. The solar thermal is simply collecting hot water, and to put that in some sort of comparison, I think this building has 55 kilowatts of PV panel on the roof, so we need to double that in order to just provide electrical power for lights and fans in the building, with a very heavily optimised system of lighting and fans in order to allow us to run the building through an annual cycle with the energy we collected from the roof. So the solar thermal at the front here has an array which has an unusual property of being able to track the sun without moving parts, and I'll digress onto that momentarily. We've been talking about cost, and we've been talking about availability as the two key components of each area in the energy system. So in terms of energy collection or energy production, we have the capital cost, but we also have the cost of maintaining that through the life of the equipment, and the total life of the equipment then being divided into the cost per annum. So any solar thermal system which has moving parts almost always becomes too expensive. You simply cannot collect enough energy to justify the cost of, first of all, building and then maintaining it. So my starting point was I needed a system that was was fixed, not moving, and that we then developed a geometric system for allowing us to reflect the sun onto the collector through an extended period of the day, so that some part of the collector is always receiving reflected as well as direct energy, and it's enabled us to extend the envelope of energy collection to the point where the solar thermal energy that I collect can be stored as hot water in the building and used to drive the air conditioning system. So we have around 100 kilowatts on the roof. We have around 100 kilowatt hours of usable battery life. It's a 200 kilowatt hour battery pack, but we don't discharge it below 50%. And I have about 700 kilowatt hours of solar thermal storage as hot water in the building. The big problem in South Australia is not keeping the building warm in winter, although that's important. The problem is getting rid of the heat energy from the building in the summer. And in round figures, it's about 3 times as much heat energy that I have to expel in the summer as compared to the heat energy I have to put in the winter. And so the next fundamental issue that I faced was, how do we achieve an internal temperature less than ambient and sustain that temperature for extended periods of time without resorting to a mechanically driven reverse cycle conventional refrigeration system, as indeed almost every building in the city will currently be running. We looked briefly at using direct evaporative cooling, and as all the engineers in the room will know, if you cool air by evaporating water, so a wet bulb type or wet box evaporator, the wet air is sufficiently unpleasant as not to be usable in a commercial context. So we again diverted for a little while and developed a system for drying the air drying the air and cooling it at the same time with a solar thermal powered system. So we were then able to collect a large amount of heat energy in the summer, store that effectively and cheaply, and then use that to dry the air coming into the building. And I also store cooled in the form of very large tanks of cold water that I use to keep the internal temperature of the building somewhere under 26 degrees. We use very large radiant surfaces inside the building, so every floor or ceiling is a radiator that radiates slight coolth in the summer and slight warmth in the winter. And the perceived temperature of the building is, as a result of that, quite comfortable, although the air temperature varies by a greater range than would normally be the case in a conventional refrigerated building. So under the building we stored around 400,000 litres of rainwater, because ultimately the energy out of the building is removed by evaporating water and then using the cold water collected as a result of that to do the building cooling. So it's an indirect evaporative system. that consumes around half of the rainfall that falls on the roof each year. So even in South Australia, which is a relatively dry place, we can collect enough water during the year to do the evaporation that I need to drive all of the waste energy out of the building by latent cooling. So I was able to construct the building. It's around 3,000 square metres of usable space. The cost of the building was a little less than a conventional build because HVAC in general terms is around 15% of the total build cost, and we were able to do our evaporative and solar thermal powered system for a little bit under 10%. So the building was a little cheaper, and it's much, much cheaper to run. In fact, I have no grid bill because I'm not connected to the grid. I looked at connecting to the grid to see if I could give them my excess energy, but they wanted quite a substantial sum that I'd have to pay them for them to decide if I could connect or not, and then they wanted me to pay a penalty each year for being connected to the grid. So at that point I thought, no, I'll just stay off grid, and 2.5 years later I'm very happy with that decision. There are short periods of time in the middle of the winter in Adelaide where it's quite cloudy for several days at a time, and so we have a small, meaning 10 kilowatt gas power generator that we run for around 250 hours a year to top up the batteries so that they don't go to an unacceptably low level. So with that rather extended process of development, starting with waste hot water and then working out how we could dry and cool air and then store both cool and heat in the form of water as opposed to energy, we have been able to construct and operate a building that is very comfortable internally and is completely off-grid. And we think it is the only solar thermal hybrid building in the world that's currently constructed. The lessons that I learnt in doing that allowed me to minify the process and take it back to a residential level. And so our next project was whether to see if we could build, sorry, I'll go forward a little bit, see if we could build a system that would operate at residential level. So we looked at the history of buildings and how things had changed progressively, and we thought that we wouldn't be able to go back to the 1880s and have a DC war, that we would indeed need to move forward. And my aim was to create a construction system that would be affordable, both in terms of its capital cost and its running cost, and thereby provide accommodation to large numbers of people who currently cannot afford to live in a comfortable style. So we have a large number of people in Australia who are either bed surfing with an aunt or an ex-husband or ex-wife or their brother or sister, and those people would all be more comfortable if they had their own home. And so that's our aim, is to build modular homes. We build them in the factory. They're designed so they can be flat packed and taken anywhere around the world. We use the same strategy of energy storage, and if I just jump forward, I use the whole fabric of the building as the radiator. So in the summer the walls are cooled, or the underfloor area is cooled, and in the winter similarly they're warmed, and that allows large surface areas and therefore small deltas for the engineers in the room. So I can operate on a delta of 6 or 7 degrees and effectively pump energy in or out of the building. That allows me to use my low-grade solar thermal energy for winter heating, and it allows me to do latent cooling in the summer without using electricity. So under the floor of these residential houses, we've adopted a similar strategy to the large building. So under the large building, I've got roughly 500,000 litres of water, and under these smaller, much smaller structures, I've got something in the order of 5,000 to 10,000 litres of water, which acts as thermal storage under the building, and that moderates the temperature inside the envelope quite rapidly. And then we use air passages through the building, which are the natural plenums created, for example, by floor spaces or wall spaces, and in that way we can deliver energy through the building. Does it work in practice? I built the big building to prove that we could, and here is our very first from the factory small building. So the materials all come in widths that can be delivered on a standard trailer or truck. You'll see that the modules are constructed, jumping forward, modules are constructed in the factory and delivered on trailers. You can see here the 3 sections or 4 sections being plugged together, and 3 days later we've got a little house. So the message in Australia is if we can reduce the on-site build time, we can reduce the cost. If we can reduce the energy consumption of the building, we can change the paradigm, because we don't need all those interconnectors, we don't need that massive solar wind farm, We don't need those huge batteries, really, extraordinarily large batteries. If we're going to keep running society the way we do at the moment, where energy is always available in effectively unlimited amounts whenever a consumer turns on the light switch. So if we, over the next 50 years, aim to move to much more energy efficient buildings, which are both affordable to build and affordable to run, we can change the total demand of the energy system and therefore make it more affordable for the entire community. I've scooted through the presentation just in the interest of time, but I'd be delighted to take any questions.
I was just wondering, how much water loss do you experience within a specific example need?
Sure. So as you will know, the latent energy of water on evaporation is about 2.18 kilojoules per gram. So for every kilojoule of energy, I have to evaporate half a gram of water. So in the big building, we might use 2,000 or 3,000 litres a week. So that's roughly 100,000 litres over the course of a year. The building roof collects about 400,000 litres. And we have enough storage, therefore, to run us right through the summer without placing any demand on the Murray River. If we scale that down, it's certainly possible on smaller buildings. The problem in a big building is that the surface area is large, like an elephant, and so getting rid of the heat is the big problem. In smaller buildings and residential buildings, of course, we can open the windows or the doors in the evening and take advantage of the substantial natural cooling. Many buildings in South Australia have a large thermal mass, so they're built of stone, for example, the very old buildings. That thermal mass is an advantage in the first day or two of a heat spell because it takes a while to heat up, but it's a similar disadvantage at the end of that heat spell because it takes a day or two to cool down. So it turns out that a better strategy is to have a building with very low thermal mass internally and some thermal mass outside the envelope that you can pump in and out at will to effectively change the thermal time scale in which the building will change temperature.
Other questions?
Are you extending your thought process on these affordable houses to also like the gardens surrounding them and the effect that can have on integrating with the housing thought?
Yeah, it's a very good question. So vegetation is vastly underrated as a means of keeping the microenvironment cool. And similarly, solar heat gain is largely given as a problem by the architect to the engineer to solve. And so, this building probably is one of the best in town in terms of the shading that's naturally provided. But a metre of glass facing north in the summer in Adelaide will collect at least a kilowatt and sometimes more than that of energy. And every kilowatt that you collect, of course, is a kilowatt you have to pump straight back out of the building again. So I didn't dwell on it, but the fluid solar large building has entirely shaded windows, with the exception of some very small areas facing east and west for early morning heat gain. So designing the envelope of the building such that a passive system works is an essential precursor. So to some extent, the engineer has to drive the architect and not the other way around. I know that's sort of like a...
that's more political than state government. Other questions? Look, I want to say thank you very much to all. Well, we had a great evening, and again, I want to thank ProManage and United Communities for this fantastic venue. And it's been amazing to see discussions from professionals at one end, high-rise buildings like this, the greenest building in Adelaide, one of the most inspirational buildings ever built in the world. The other end, a gentleman suggesting we should all go off-grid. Then we've got another speaker from Tasmania suggesting we need not one interconnect between Tasmania and the mainland, but 4. 2 via King Island. I think you've got relations there. But, we hear how the state government in South Australia is leading the world with renewable energy. And we hear from one of the greatest, ironically, French-owned companies who's doing wonderful things in not only South Australia, but Australia. So once again, I want to thank ProManage for sponsoring tonight. providing us with the most wonderful venue I think I've ever been in. And I think from an energy perspective, we've heard some discussion tonight that is frankly inspirational. So thank you very much for coming tonight. Final statement, I see it probably the largest audience I've seen for an IET event in the last 4 years. And I want to spend a little bit of time talking about the IET. It's called the Institution of Engineering and Technology. It's been around since about the mid-1800s. It's headquartered in London. We started off offering membership to engineers, but now it's really to STEM, or should I even say STEAM professionals. If you're not a member of the IET, I seriously want you to consider becoming a member. Because these events are sponsored by very hard-working volunteers like Gail Jackman, like Gary Neve, like Majid Awadallah, like Clinton Sewell, like Rob Peitland, like all the members who are here who have made this event happen tonight. We need more people like yourselves who have come along tonight to join our organisation and put some power behind what we do. If this is what a handful of volunteers can do, just by being creative and thinking and working together, imagine what could happen if there was 100 of us doing it. And I'd love to see every one of you here consider becoming a member, and really, I want the Chief Scientist as our primary member. Thank you very much.
In the interest of sustainability, as people leave, you can leave your name badges because we don't want them to be single-use plastic. So you can put them on the table so that we can reuse them for our